Welcome to our video for Roundup 2020. We're going to try to show you some STEM activities to go along with Roundup this year, so we hope you enjoy it. My name's Rick Clovis. I work with OSU Extension in Pawnee and Osage County, and with me today are
Stacy Dawson with Osage and Washington County.
And I'm David Adams with Parks and Recreation Department in Muskogee, Oklahoma.
So what David's got there in his hand, we're going to use liquid nitrogen today that we've got here in this big can below, but he's just got a cup full of it there. And you can see it's pretty steady the way it is, but we're just going to use it to show the different properties of elements. David can actually boil the liquid nitrogen with his hand. The heat from his hand is boiling it, which is, we would think his hand would be burned, but show him your hand. It's not burned because it's tapping at a different temperature than we're normally used to. Like, to boil water, it has to be at 212 degrees above Fahrenheit. Liquid nitrogen stays a liquid at 321 degrees below 0 Fahrenheit. So David's temperature of his hand, just his 98-degree hand, is actually boiling that liquid nitrogen. So those things are happening at different temperatures to different elements depending on what their properties are. So that's kind of the main thing we're going to talk about today is phases of matter. There's 5 main ones. The one at the coolest end of the extreme is called a Bose-Einstein condensate. It's very rare. It hardly happens here on Earth, but you have to get down to near absolute 0 on the Kelvin scale, which is like 460 degrees below 0 Fahrenheit. So that's really not something we're going to be able to show today, but there's lots of cool YouTube you can watch on that. And the next one up would be the next warmest, would be a solid, like we have in water. That would be ice, water, and then a water vapor. So all elements occur in that same order. So we'd have the solid, then a liquid, and then a gas. And then the hottest one is called a plasma, and we're not really going to be able to do that today either, but like in nature, the sun would be plasma. The northern lights are plasma, and magnetic fields reacting together. Fluorescent lights, neon lights, those are plasma. So we're going to use we're going to use liquid nitrogen to show you some of those properties today, and hopefully you'll enjoy these experiments. Thanks.
Okay. All right, we're glad to get started today with our workshop for Roundup 2020. What we're going to kind of talk about today is trying to show you some things that happen outside the normal world that we're used to experiencing. I mean, living here in Oklahoma, the normal temperatures that we see, somewhere in the teens or, single digits in the wintertime to maybe 105 or something like that in the course of the summer. But the liquid nitrogen that we're going to talk about today is negative 321 degrees. So 321 degrees below 0. So we think about that with water. Water has been a solid for nearly 350 degrees by the time we get to the point where nitrogen, which we breathe every day, is all around us. Nearly 3/4 of the atmosphere that we breathe is liquid or is nitrogen. The only thing that's different about this is we have refrigerated it. It's now from room temperature. We've taken it down. We've taken all of the heat energy out of it. And that's what makes it fun to do some experiments with. So we got plenty of experiments that we're going to do today. And the first one I want to show, this is just a teapot. Many of you probably seen something like this. You put it on the stove, you boil water in it, and when it whistles, it means that the water's hot enough to pour over our tea, and we can make some of that good Oklahoma sweet tea that most of us like to drink anyway. I know I sure like to get a sweet tea. So, like I say, the weird thing about this is the temperature that we're dealing with. So we would never think about a teapot sitting on the counter whistling, because whistling is what makes, the phase change that's happening with water as it goes from 211 degrees to 212 degrees and it begins to boil. It goes through that phase change, and the whistling doesn't have anything to do with tea other than we can be doing something else in our kitchen, and when it starts making that noise, we know to turn around and pour it over our tea, that we've got that our temperature's up. But we can even boil that, so it's steaming, and it's so cold you can't even hold your hand on it. You can get frostbite if you held it, but it's steaming. It's got boiling coming out of it. It's steaming cold. Is that even a thing? Anybody ever heard steaming cold before? But we got tons of little experiments like that. We're going to clip them together today, and hope you're entertained. And there's something about a meeting that happens after this.
Yes, there's going to be a follow-up Zoom once you finish watching all the pre-recorded videos. There may be questions throughout the videos, so watch for those. Rick and I may have some questions for you, but make sure that on your designated day that you show up to your Zoom meeting that follows you watching the pre-recorded videos.
All right, so we're going to show you the power that comes along with phase change when elements start changing phases, the energy that is released when doing that. Robert Fulton discovered this with the steam engine he used wood or coal to heat water and contained that expansion of the water from a liquid into a vapor and used that to power steam engines. A man named Herodian originally came up with the process. He was a Greek dude way back in BC sometime, 1,000 years BC or whatever. He came up with a hero engine where he had a metal round pot and he had two little vents sticking out of it and they at different angles, and then he would heat the water up in there and make it boil, and it would cause that hero engine to spin. And we're going to do the same thing with water bottle. We're going to show you the power that can be released when elements go through a phase change like water boiling from a liquid to a gas. Instead, we're going to use liquid nitrogen, and we're going to show you the power even in it at 321 degrees below zero, how much power it can release. We've got this liquid water bottle. We're going to make a closed container when we put the lid on, but it's got these little holes in it, jets that will shoot out this way, and then the other one that will also shoot out that way, causing it to spin. So we're going to show you what that looks like. So there you see, just imagine how much energy can be released when you use something like water, heating it really up. The hotter something is, the more energy it's going to contain. That was just a half a cup of liquid nitrogen, 321 degrees below zero. It made this spin that fast. That's why we can use steam energy still on our submarines and aircraft carriers today. They use steam engines, just they use nuclear fuel to heat that water. So hope you enjoyed that.
All right, I have a bucket of liquid nitrogen and a very big concrete floor. We've moved out into one of the hangars in Muskogee in our livestock show arena, and so about half a bucket of liquid nitrogen. If we think about what would happen if we threw water or dripped water onto a pancake griddle, this is kind of the same thing. The liquid nitrogen is going to want to boil as soon as it hits this floor, and it's going to form a gas layer underneath it, just like water does. It forms that gas layer and protects the liquid part from just flash boiling away. So this should, as we throw it across the floor, just form these kind of moving bubbles of water that are going to want to go skating across this floor. They're not actually touching the floor, they're floating on gas, on a layer of the liquid nitrogen. But we're gonna have some fun here and just see what happens. Are you ready, Rick?
Ready.
Okay, so some of this stuff is kind of different. Like I say, it was always a liquid going across here, but you can almost see how the water, the liquid part of this, of course it's liquid nitrogen, it's not water, but we can imagine how water would impact some of this, and it pulled the dust together in the floor in these piles before all of the liquid nitrogen evaporated away. None of this was this, it didn't have this pattern. You can almost see over here how it looked like the water went through, liquid nitrogen went through and picked up the dust and carried it with it into these puddles. So it's just kind of an interesting experiment. Shows that how the water, how I keep saying water like it's a thing, but it's not water, it's a liquid nitrogen, but it behaves so much like water, and that's what we're showing. It's just how things change and how they relate to what we're used to, and how they change, and they are not always what they seem.
So for this experiment, we're going to blow up a balloon using liquid nitrogen. So we're going to pour the liquid nitrogen that's in here into the pop bottle. And once that's in there, then David's going to put the balloon
A little bit's
a
good.
little bit more.
Another little splash, you know.
Never hurt anything.
Except that one guy in Terminator.
So what he's doing by doing that is he's putting a cap on this so that there's going, like, the number of molecules that are in there are going to stay constant throughout the whole thing.
And that's the balloon breaks.
So let's put our experiment back together and we'll talk about solids. Well, we'll let that go ahead and fill up. So hot summer day, we're all bouncing apart. We're way back because we don't like being close to one another, so we're in a gas. Cool October day, we're more like a liquid because we're a little bit closer. Our molecules aren't bouncing off of one another with as much energy. We get to like a January day when it's cold and rainy. We're all just kind of bunched up. We're not moving. We don't mind one another to be close together because we're just trying to keep some warmth. We're trying to stay, and that's more like a solid. So those are our three phases of matter that we deal with kind of primarily. We can talk about those fringe ones. You know, that guy we know, Rick, likes to talk about those fringe ones that are really, really cold and really hot. But the three that we normally deal with are solid, liquid, and gas. And it looks like our balloon, we locked it back in. Let's see if this one stays. I'm gonna hold on to it. I'm gonna get my safety glasses on because getting with the balloon is never good. We're gonna make it boil good.
The anticipation is killing me.
I know. You should be holding on to it. Let's see. I still have a bucket of water. I still have a bucket of water. Wow. God.
You're on.
In this experiment, we're going to show a little bit about how the liquid nitrogen reacts when it hits the air. And for us, this room is just a normal, like 72 degrees. So to us, it's a comfortable room. We're here. If we do anything with water, all it's going to do is splash. So let's prove that just a little bit. So I have a pail of water or a bowl of water here, and then I have some liquid nitrogen that's in this cup. And even just moving it on the table is so hot, because remember the liquid nitrogen is negative 321 degrees. This table is room temperature. So there's a 400 degree difference between the table and the liquid nitrogen. So if we think about what we would do, like dropping water onto like a pancake griddle or something like that, pancake griddle may only be 375 degrees. So really that's only a 300 degree difference between room temperature and the pancake griddle, and we have a 400 degree difference between the table and the liquid nitrogen. So it's kind of hard to wrap our mind around that. So let's see what happens if we do some of that. So what we're going to do is we're going to smash some cotton balls that have liquid nitrogen in them and a cotton ball that has water in it. So sound is one of the key things that's important in this experiment. So we're going to try to get an idea about what sounds we're hearing and what we're listening to. So if I just take the rubber mallets and I just hit them together. So that's what I get for sound. Just a kind of a nice, low clapping sound. And then, all right, so I'm going to take a cotton ball that has water in it, and I'm going to hit it. And what I'm expecting is for that water to go spreading out across the room. And I heard a smack is I don't know if that's out of frame or not, but you can see some that hit over there, some that hit my shirt. The cotton ball just basically exploded and went everywhere, and the water shot out in a big pancake pattern around it. So, but there really wasn't much sound. There was a sound of the thump of that styrofoam being hit, but really pretty similar. So I'm going to shake some of the liquid nitrogen out of this. Got it sitting on there. It's got water vapors coming off of it because it's condensing. So let's do it one more time. See if you heard. I heard what I was listening for. Let's see if you can hear it this time. Oh, in that case, hopefully it came through on the video, but you should have heard more of a pop, is that just like in the water, the liquid water went shooting out into the room, but it did nothing because water is right in its sweet spot. It's still in a liquid phase from 32 to 212 degrees Fahrenheit. The liquid nitrogen is not. It's still at the 321 liquid phase inside the cotton ball when we hit it, and it goes shooting out into this super hot room that's got 400 degrees warmer than its boiling point. It rapidly expands and we get the pop that is formed. So, if you got any questions, hit us up on the Zoom after the show.
What you just saw was a time-lapse video of some phase changes that the balloons underwent when we put them in liquid nitrogen. When we put them in liquid nitrogen, the molecules that were inside stayed the same, but they turned into a liquid. So when we put them in the liquid nitrogen, this was the shape that they were. So it's kind of hard to tell, but there's some liquid, it's right there, but there's some liquid that's in there, and what's going to happen is that goes back to room temperature, those molecules that are in there are going to start expanding again, and then once they expand to their normal size, we'll have the balloons back to the size that they were when we started.
Talked earlier about how materials and elements change their properties as we warm them up. They change their physical characteristics, like when they go through the phase changes of a solid to a liquid to a gas, but they also change some internal properties like the conductivity. Here in this half disc, we've got a superconductor, which is made of yttrium, barium, copper oxide, and it's one of the easiest ones right now they've developed to become a superconductor. You see right now at that room temperature, and David just put a neomagnet on it, and the magnetic field is not changed. It just sits there on top of the superconductor. But now we're going to cool the superconductor off with liquid nitrogen and take it down to negative 321 degrees, and we'll see what changes there. See that the superconductor is still warmer than the liquid nitrogen, boiling it off, but in a minute the liquid nitrogen will overcome that and cool the superconductor down to its temperature of negative 321 degrees Fahrenheit, and we'll see what changes as that happens. Watch the magnet. And there you see it floats up. It's in quantum lock now, it's called. The properties of the superconductor have changed. The magnetic field is actually going through it, and because there's less resistance as it cools off, and it even spins there in place and will just stay right there as long as we keep it cool enough. And that's why they use that for the bullet trains. They're trying to develop computers that can use superconductors so they don't build up the heat and will be faster. Now David's taking it out, and we're going to warm it back up and see how, as it loses that property of superconductivity when it's down at room temperature. And that's one of the challenges of developing superconductors, is having them work at some manageable temperature instead of liquid nitrogen temperature of negative 321 degrees. Hey, that's the end of our first video. We've got so much cool stuff we couldn't fit it all in one video, so we're going to do a second part. So check the schedule for that second video. We're going to do more experiments with liquid nitrogen, talk about phases of matter. We're also going to have a follow-up Zoom to both videos where we're going to take questions. We'll do a few more experiments, and we'll do a survey as well, see if you learned anything. So we'll see you at that second video.